Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem maximum stone removal. So the question states there are n stones at some integer coordinate points on a 2D plane. Each coordinate point may have at most one stone. You need to remove some stones. A stone can be removed, very critical. A stone can be removed if it shares either the same row or the same column as the other stone that has not been removed. Now, given an array of stones, which represents the ith stone, return the maximum possible stones that you can remove. Now, the critical thing was you can only remove a stone if it shares a row or a column with some other stone. For an example, I can say if I take this stone, this can be removed because this stone shares, it doesn't share a column with any other stone, but it shares a row. If you see this stone and this stone shares a row with each other. So what I'll do is I'll go ahead and say I will remove this. So I'll cross it off. So one stone I have removed. Okay, one removed. Next I can say, hey, can I cross this off? Let's think about this. Can I cross this off? I can because I know on this row we don't have any further stones because this is removed. Currently on this row we do not have any further stones. But can I say over here, if you see, there is another stone. Thereby, I can remove because this column has another stone. Perfect. Again, over here, this column does not have any other stone, but this row has one more stone. So I can remove this as well. Now, coming across, can I remove this? Let's have a quick check. No, no, because this is already removed. So we cannot. Now, can I remove this? No. Yes. Yes, because there is another stone. Go ahead and remove it. So apparently, can I say at the end of the day, there are two stones left and you are able to remove one, two, three, four. So the answer to this will be four. You are able to remove four stones right at the end of the day. Let's look at one more example. Can I say over here, this cannot be removed? No. Can I say this cannot be removed? No. Can I say this can be removed or this can be removed? So let's quickly start off by removing this, right? So I can say this guy shares with this. So let's remove this. Perfect. Next, I have this. This shares with two other guys. So let's remove one more. Again, I have one more, which can be removed because shares with one more. Can this be? No, no. So apparently, three left, but I was able to remove three stones at the end of the day. You can try out every other possible configuration, but you'll not be able to remove these stones because they do not share a row or a column with any other given stone. So let's not think about any of the algorithm as of now. Let's look at the thought process, maybe do some dry run, and then figure out which algorithm will be used. So we see, okay, kind of, can I say I can connect these guys? I can. Can I say I can maybe connect this? Yes, I can. Can I say this and this? Yes. So somewhere down the line, can I say connected, connected, connected? Can I say this? Yes. So can I say there are four stones which are ideally like connected? Can I say this? There are four stones which are connected. I can. And if I go across removing, I can remove one, two, three. But I cannot remove the last guy out of all the connected guys because he will have no other stone remaining. This guy will get this guy. This guy will get this guy. This guy will get this guy. But when you try to remove this, since all of these are removed, he will not get anyone. Okay, makes sense. Now over here, again, if I try to connect it, it's like a connection, right? So again, if I try to remove, I cannot remove both of them. So I can actually remove just one of them. Correct? Okay. Let's look at one more example. So over here, this guy, no connections, single. This guy, no connections, single. So let's look at these guys. Can I say this guy, this guy, this guy, this guy, something like this? Yes. So thereby, I'll be like, okay, 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 connected, connected, connected. Can I say I can remove this, 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 but I cannot remove the last guy? Or I can remove this, this, this. I cannot remove this. Whatever I do, I will not be able to remove one guy. That is for sure. correct? So these guys cannot be removed. So can I say that if I can somehow connect these guys, the answer is going to be pretty simple, right? If I can somehow connect these dots, the answer is going to be pretty simple. What will be the answer? Can I say the answer will be whatever is the component size of this, whatever is the component, like whatever the number of stones are there, that is 4 minus 1, because I cannot remove 1 for sure, but I can remove 3. And can I say over here, I cannot remove 1, but I can remove 1 because total was 2. So in total, I can remove 4. Can I say this? I can. Over here again, can I say, over here, if you see, the size of this is 1. So 1 minus 1. Again, the size of this is 1 minus 1 because this is the component. You cannot remove one guy. Apart from that, you can remove everyone. But he's alone, right? Again, there are 4 guys, but I cannot remove one guy. So can I say I'll be removing 0 plus 0 in the first 2 sets and then 3 people, which makes it 3. Can I say this? So can I say this is somewhere boiling down to a connected component? Like I can assume this stone to be a node, this stone to be a node, this stone to be a node, this stone to be a node. Can I say this? I can. I'm not going to the implementation details as of now. I'm just assuming these stones to be the node of the graph. Can I assume this to be a component in a graph which has 4 nodes? Can I assume this to be a component in a graph which has 4 nodes? Can I assume this to be a component in a graph with single nodes? I can. So thereby, what I will say is, if I can assume them to be components, so can I say, in short, if there are n stones, and there is component, let's say component 1, component 2, component 3, and the component 1 has x stones in it, like something like this. Assume this was the component. So how many stones are there? 3. So x becomes 3. Assume over here there were 2. So here I can say there are x2 stones, and over here x2 will be 2. Over here x1 will be 3. Similarly, I can say component 3 which will have x3, component 4 which will have x4. I did take these examples, you can remove them. So if I write in terms of x1, x2, x3, can I say overall x1 stones, x2 stones, x3 stones plus dot 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 will be equal to n stones? Because these are individual components. If you sum up the individual components, that will be the total number of stones. I definitely know that. What is the answer of stones? Like how many stones are removed? How many stones are removed? I know in a component, I can remove everyone apart from one guy. The last guy will be alone. He doesn't find anyone in the row or in the column. Can I say it will be x1 minus 1 plus x2 minus 1 plus x3 minus 1 plus x4 minus 1 and so on? I can. Now, can I write them as x1 plus x2 plus x3 plus dot 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 dot? And this minus 1, minus 1, minus 1, minus 1 can go out common, right? So thereby, can I write this as x1 plus x2 plus x3 plus dot 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 minus taken out common 1 plus 1 plus 1 plus 1 from all the components. From all the components. So can I say this is nothing but it's taken from all the components. We already proved this value, which is yes, n, which is the number of stones minus, what is this? Taken. 1 is taken from every component. Can I say it's nothing but number of components? Yes, this is your answer. You need to derive it. The answer is very simple. N minus number of connected components is what you need as your answer. So the question boils down in a 2D matrix, where the row and column are connected, and the row and column are connected, you have to figure out the number of components. Once you figure out the number of components, the question boils down to n minus number of components. So if you go back to the example, this example, 1 stone, 2 stone, 3 stone, 4 stone, 5 stone, 6 stone. The answer was 6 minus the connected components. 3 components were there. So 3. Over here, 1, 2, 3, 4, 5, 6. 6 stones. How many components? 2. 4 stones can be removed. Quite simple, isn't it? Whenever you hear about connected components, which algorithm comes to your brain? Either you say we will do something like a traversal algorithm and apply DFS, BFS, or you say we have a disjoint set data structure which helps us to connect people. Because over here we are connecting, over here we are connecting, over here we are connecting. So it's about connection. So in connection, we do not use traverses. It doesn't make sense. Whenever you are connecting two stones, the proper algorithm to use is disjoint set data structure. Don't know about it? I've already taught you in this particular graph series. Go back and watch it. Go back and watch, come back. Pause this video. Do not watch the video afterwards because you'll not understand anything. So what will I do? I know one thing. I can say these two guys can kind of belong to the zeroth row. Can I say this is an entire node where I have two people? I can. Can I say a row is a node? A row is a node in the disjoint set. Till now you know how is disjoint set. 1 itself parent, 2 itself parent, 3 itself parent, and so on. Can I say that I will treat a row as a node? Yes, I will treat a row as a node. And that is very simple. So I'll be like, okay, I have 0, I have 1, I have 2, I have 3, I have 4. So these are my rows which will be treated as node in disjoint set. Very simple. If there is a stone, I say it belongs to node 0. If there is a stone, I'll say it belongs to node 0. Right? Very simple. So now, then how will you treat the columns? We'll say we'll treat the columns as the next set, and they will be again treated as nodes in disjoint set. But how do you treat column? Because you have 0th column and you've already used 0. So if you're using till the 4th index and there were 5 rows, So can I say post 4, the 5th guy can be treated as the 0th column, the 6th guy can be treated as the 1st column, the 7th guy can be treated as the 2nd column, and the 8th guy can be treated as the 3rd column. Can I see this? I can. It'll be like 5, 6, 7, 8. These 4, you just do a coordinate mapping. 0th column will be treated as the 5th node, 1 column will be treated as the 6th node, 2th will be treated as the 7th, and the 3rd will be treated as 8th. Just did a coordinate shift. How much did you shift it? Can I say you shifted it by column plus whatever is the last value over here? This is the last value. Column plus 4 plus 1. Because this is 5 is where you start and the column was 0. So 0 plus 5, the first time it went here. Next, 1. So 1 plus 5 went at the 6. 2. 2 plus 5 went here. So I did a shift by column plus 4 plus 1. That's it. And you can have the disjoint set data structure. Now, let's quickly implement the disjoint set data structure. Now we know we have 0th row, 1st row, 2nd row, 3rd row, 4th row, right? And we know we have the 5th column, which is the 0th column, 6th, which is the 1st column, 2nd column, and the 3rd column. We know this. So we have all these nodes which are individually alone as of now, right? So let's quickly start. So we are saying there is a stone on the 0th row and the 0th column. So anything on the 0th row and the 0th column will get combined. 0 row and 0 column get combined. You don't combine stones. There's no point in combining stones. You take everyone with you. So you say anyone here and anyone here. Just go and connect. I'll be like, okay, fine. So I'll be like, okay, 0, that's this row. Can you go ahead and get combined with the 0th column, which is the 5th? So you'll just go ahead and say, okay, let's take this and connect it with the 5th. Okay, perfect, amazing. So what's the next thing? Next stone is here. So it's at the 0th row and the 2nd column. What is the 2nd column? 7. So you say 0 and this one, please go and get connected. I'll be like, okay. So I will just connect these guys and I'll just omit this. Nice. Next, which is the stone? Here's a stone, which is at the 1st and at the 3rd, which is 8. The 1st and the 8th will get connected. So go ahead and connect it. Perfect. Done. What's the next stone? Here. So 3 and the 0. So 3 and what is 0 for you? Is 5. Is 5. Did you realize what happened? What is 5? Its ultimate parent is 0. So this 3 goes and gets connected to this. Again, I'll repeat. This was at 3. 3 was this. This is 0. 0, is treated according to this formula. 0 plus 4 plus 1, 5. 5's ultimate parent in disjoint set is 0. So 0 and 3 will get connected. So connect 3 to it. Did you see how efficiently all of these guys got connected here? If you carefully see, right? Next, which is the next one? Next one is this. If you carefully see, where is it? 3 and 2. So basically 3, which is this. What is 2? 2 is nothing but 7, which is already connected. No need to do it. So done. So once you have done this, what is the next job? The next job is very simple. It's the last one. So it's at the 4th. It's at the 4th. And it's at the 3, which is the 8th. Okay, 8 is here. So 4 goes and connects here. And this will be over. So after the dry run, if you carefully observe, this is one of the disjoint set. This is another. And this is another. And this is another. Right? Let's analyze. This is the row 0. Who is the ultimate parent? It's connected to column 2. Okay. It's connected to row 3. Okay. It's connected to column 0. Okay. Everyone gets covered. So understood. Next, row 1. Where's row 1? Here. Connected to row 4. Let's see. Okay. Connected to column 3. Makes sense? Because if anyone was here, it would have got into it. Okay. Next, row 2. Let's look at row 2. Oh, doesn't exist. It's connected to no one. Column 1 doesn't exist. No stones. So, can I say, I kind of can discard these guys and I can say there are actually 2 valid disjoint sets, like 2 valid parents. There is just 2 valid parents. So, if there are 2 valid parents, can I say there are 2 connected components? I can. So, how do you figure out the valid parents? It's very simple. Just take the stone and look at its ultimate parent. Like for this stone, the ultimate parent of 0 or this 0 will be this. For this stone, the ultimate parent will be this. For this stone, the ultimate parent will be this. For this stone, the ultimate parent will be this. So for all these stones, there will be one ultimate parent, right? So you can just keep a count. I'll tell you how to implement. Then for these guys, there will be one ultimate parent. There will be 2 unique ultimate parents for all the stones. For all the stones, there will be 2 unique ultimate parents. That's it. If there are 2 ultimate parents and there were like 6 stones, 6 minus 2, 4 is the answer. The implementation is going to be very, very simple. Don't worry about it. So I hope you have understood the entire explanation. Now it's time to code it up. So I'll be coding the C++ solution on the right and you can figure out the exact similar Java solution on the left. So given the stones, we're given the n, but no one is saying us the size of the grid. So what we will do is we'll kind of figure out where's the last stone in the grid on the row. That will kind of give us this length. I'll figure out where's the last stone in the column. So that will also kind of give us the dimension of the grid. So I can probably keep it as max row equal to 0. And I can probably keep it as max column equal to 0. And I can iterate on the list of stones. And I can say max row will be max of max row, comma, like wherever, like whatever is, whichever row the stone is at. And max column, comma, ID1. So in this way, we can figure out the dimension. So we have the last index. Yes, that's the last index where the stone is. So that's the grid. So what is the next thing that we require? We require the disjoint set data structure. If you remember the previous lecture, I've already given you a snippet of code which can be reused in almost every problem. So I'll just go ahead and maybe copy and just paste it here. Okay. And maybe just hide it. Yeah, all the functionalities. Perfect. So this is the disjoint set code snippet that I've been reusing. You can watch it out from the previous lecture. Now what's the next thing? We need to declare the disjoint set, correct? So can I say disjoint set ds? What will be the size? That's a big question. So if you remember, the first were the number of rows and then were number of columns. So can I say the total nodes will be rows plus columns? Yes. So it will be like max row plus max column. Let's take +1 for safety reasons. You'll not require, but yeah, let's still take +1 for safety reasons. Perfect. So this is something which I have already taken. Now, what is our next job? We know for every stone, we say this row and this column, combine yourself. So, okay. So auto of IT, I'll go across the stones again. And now I'll be like, I know the node for the row. What will be the node number? It's going to be simply whatever is the row. Because if you remember, row was 0, 1, 2, 3, 4. But the column started after that. So for the node column, I will have to go like, it's the normal one, but it will repeat itself. Like it'll overlap with the rows. So I will have to go one after the max row. Whatever is the max row, I'll just have to go one after that, right? So I take one after that, and after that I can just keep on going. And I go ahead and say, hey, listen, can you go ahead and say ds dot union by size? Please go ahead and combine them. That's it. Just make sure disjoint set does it. Once this is done, I need the unique parents for all the stones. So maybe you can have a set, or you can have an unordered map which will kind of have the unique rows and columns, like unique nodes. That's one of the ways to see it, like map of int comma int unique nodes, because all the nodes will not be generated. I'm just taking the nodes where the stones are, or you can say the stone nodes. Like if you remember the dry run, I showed you all the columns, but over here only the nodes which are present in the disjoint set will be there. So you can probably say stone nodes equal to the node row. This is there, and stone nodes, and you can say node column is there. Perfect. Once you've done this, you need to count the connected components. So you can go ahead and say count 0. And for auto off, you can just iterate in the map, and the map is stone nodes. So not stones, it is stone nodes. And in the map, you can say, hey, listen, if ds dot, you can just take the find ultimate parent. Find ultimate parent of this particular guy. And remember, map will just store unique rows, or like if in a row there are multiple stones, then also it will just store one node. So this is basically storing which nodes are there in the disjoint set. Find parent of id dot first is what the node is. If this is equal to the node itself, so it is the boss, then you count it. Number of boss counted, the answer will be number of stones minus the number of connected components. And if you do this, and if you go ahead and compile, this should be running absolutely fine. Indeed, it does. And let's quickly submit this and see if it is running fine. I am too proud of myself. I'm writing codes without any compilation errors, and it's submitting at once. So you saw how easy was it. Once you know this particular snippet, it's just reusing this. It's a bit of constructive thinking. And once you have this constructive thinking, you can actually implicate disjoint set data structure and can solve any problems. You will not find it tough. So before wrapping up this video, a small request. I was going through the statistics of our channel. Nearly 50% of the viewers of our channel do not hit that subscribe button. I know it's not an entertainment channel, but still it's a very, very honest request that please do consider subscribing to us. And if you have seen the video till here, do consider hitting that like button. And if you haven't checked out our DP series and the SD sheet, the links will be in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken.